Assalamualaikum warahmatullahi wabarakatuh to the ladies and gentlemen. My name is Nurgaisa binti Abakar with entry number 295214, and today I would like to present about our article. We will start with our chosen article. Okay, so this project is grounded in the article titled An Accessible Feature-Based Framework for Fine-Grained Code Quality Assessment by Ziadi and colleagues, which published on 2029. So this article focused on a major limitation in traditional software quality assessment approaches, particularly how software quality is often evaluated only at the overall system level, which means there is no like specific feature which tell them that affect the whole score. So traditionally, software quality is reported using aggregated system level metric such as overall maintainability, technical depth, and also the total bug count, which these metrics are useful for providing a general overview. They tend to hide quality problems that are concentrated within specific functional features. So, as a result, critical defects in important components like features or function are such as authentication, transaction, processing, or booking workflows may remain undetected or unprioritized. Okay, so now we move to the objective. So this study has four main objectives, which is first, it aims to move beyond system-wide metrics by proposing a feature-oriented quality assessment framework. Second, it seeks to identify feature-level quality hotspot where technical debt or security risks are concentrated. The third one, the study demonstrates how multiple analysis tools can provide complementary insights. And the final of the objective is it supports strategic maintenance decision by prioritizing refactoring based on business important rather than code metrics alone. Okay, now we move to the research methodology overview. So to evaluate the proposed framework, the authors adopt an empirical case study based research methodology. The methodology is structured into four main phases, which is starting from quality attribute selection and ending with hotspot analysis. So each phase contributes to building a detailed feature level view of software quality. Okay, in the first phase, which is the relevant software quality attributes are selected. So this study focuses on maintainability, reliability, and security, as these attributes are commonly affected by technical debt and also design degradation. So this dimension also have a direct impact on a long-term system sustainability. In the phase two, which is feature, location, and mapping. So here the source code is analyzed to establish traceability between code elements such as classes or methods and their corresponding functional features. So this step is essential because it enables fine-grained analysis at the feature level rather than at the system level. So the next quality metrics are collected using multiple analysis tools. So static code analysis tools and security scanners are used to gather different type of quality data. So these metrics are then aggregated and projected onto the identified features using a dedicated mapping tool, allowing non-overlapping insight to be combined effectively. So the tools that we use for our method, okay, for the um for this study, this article, they use like SNYK and also SonarQube. So we add one more tool which is JMeter. Okay. So the phase 4, which is the last phase, so the aggregated feature levels results are analyzed to identify quality hotspot. This analysis highlight which features contain the highest concentration of maintainability issues, reliability concerns, or security risks. So the outcome provides developers with actionable insight for targeted quality improvement. So from the methodology that I have present, our project have adapted the feature-oriented framework proposed by ZD and colleges by introducing a hybrid evaluation approach. So instead of analyzing software quality in isolations, we combine static code analysis, security assessment, and dynamic performance testing. The evaluations is conducted at the feature level rather than the system level, allowing us to observe how internal code and security weakness affect runtime behavior. The analysis focus on the staff login and room booking modules, as these are both security sensitive and performance critical. Okay, now move to the tools. So for our project, four industry standard tools were used to support these evaluations. The first one is SonarQube. So SonarQube was used to assess static code quality and technical depth, while SNYK was employed to identify high-risk security vulnerabilities. So, and next we also have Aperture JMeter was used to test system performance under concurrent user load, and Grafana was integrated to improve visualizations and static analysis result. And finally, a result from all tools were synthesized to produce evidence-based finding that link code quality, security exposure, and also runtime performance.
Assalamualaikum and a very good morning. My name is Nusha Sharina binti Abdulhamid. I'm a graduate 29553 and today I will be demonstrating our quality analysis using SonarQube. So first we started by scanning the entire hotel management that we choose from GitHub, and after we run the SonarQube using Docker, we can see the dashboard of SonarQube here that shows all the result and measures. So as we can see, the result looks promising, and the system passed the quality gate and earned an A score for maintainability. But this is quite misleading, and we call it as monarchy paradox, because if we look closer at the metrics, the reliability is C with 45 bugs, and security review is E, and test coverage is 0%. So the system may look clean on the surface, but it is actually quite dangerous. So to get a high level view of our technical risk, we go to measure tab here. So in measure tab, we can see all the metrics that we want to measure. For example, the reliability, the security, maintainability, the duplication, and all. So first we look at the project overview. In the project overview, this chart plots the technical depth against the test coverage. So the y-axis indicate the coverage and the x-axis indicate the technical depth. So we can see that every single bubble here is flatline at the bottom, which is 0%. This prove our 0% coverage problem. So if I hover to the large green bubble here, we can see that roombook.php file has 1 hour 39 minutes of technical depth and is completely untested. So this identified as a depth trap, which is a complex file that is expensive to fix and dangerous to touch. So let's move on to the next specific metrics we want to measure, which is reliability. So in reliability, we found like 45 bugs in the system. So this chart shows us exactly which file are unstable. So if I over to the big bubble here, so this is admin.php file has like 11 bugs alone. So this bug create a scope pollution where variables leaks into global scope. So this is critical architecture failure, because if the system meant to be deployed in real life, it will poses a high risk of crashing or corrupting data at the moment multiple users try to log in at the same time. And then we move to security measure. So in the security overview, this is quite tricky, because if we look at the chart, all the bubbles are green. So this means that the system has zero vulnerabilities according to basic scan. But if we look at the left menu here, security review, we have E rating for security review and 11 security hotspot. This means that while the code looks okay on the surface, but we are missing critical defense. So for example, we are vulnerable to SS attack because we didn't turn on specific security protection. So the system is not safe for real user. And then we move to maintainability overview. So in maintainability overview here, we found like 363 code smell in the system. So this chart shows which file are the messiest one. So if I hover to the orange bubble here, it shows that admin.php file has D rating. Okay, and this means that the code is um, poor quality and hard to read. So if I hover to the large green bubble here, which is roombook.php file, which contains 72 code smell alone. So this create a high quantity load, means that it takes the developers a long time to understand the code before they can even start to fix the bugs. And then next we go to the duplication. This is the duplication overview. We have like two bubble here. So the circles are the file and the y-axis show how many lines are copied. So if I hover to this bubble here, this is home.php file. It has 40 duplicated lines out of only 49 lines. So this is what we call technical bloat. It means that developers are just copy and paste the code blocks instead of writing clean. So this makes the system very hard to update. And that's all for the measure tab in SonarQube. And then we move to the code tab here. This code tab just show the like overall that we can see the line of codes, the bugs, the vulnerability, code smells, the security hotspots coverage, and duplication in more details. So this is like code breakdown. So if we look at the admin folder here, we can see that it has over 1,000 lines of code, but the column next to him is like bugs, got like 32 bugs and 320 code smells. So this proves that the biggest part of our system is also the dirtiest and the most likely to break. And I think that's all for the Sonar Cube demonstration. Thank you. Okay, let's continue. After we analyze the code in SonarCube, we want to visualize the data more clearly because we want to see the data more clearly. So we decided to develop a custom Python automation script to pull the data and visualize it on Grafana. So we decided to use Grafana. So as we can see here, this is the main dashboard of Grafana that contains 7 charts. So the first one is total issue by OAuth category. It shows 408 total issues that have been found in our system. So this aggregates every code smell and bugs into a single view. And then we have vulnerabilities over time. It shows no data. This is actually successful demonstration of API security because the API token that we use for this external dashboard is restricted. So now Cube successfully blocked the request for sensitive vulnerability data. And then we have bugs versus code smell. As we can see here, the major portion here is the green one, which is the code smell. So this proves that the code base in our system is messy. And then the next one is issue over time chart, bar chart. So in issue over time chart, we can see that the one massive solid red block sitting at 408 issues. So this is a technical wall which proves that our debt is stagnant because we have not fixed a single issue since the scan started. And then we have severity trend over time. So in severity trend over time, it shows that the weight of our problem. The huge blue bar confirm that the vast majority of our technical debt come from minor issue. And then we have total issue by severity here. We can see that the tall orange bar here, 310 issues, minor issues, mostly the messy code, but the real danger is the 4 blockers and 8 critical issues. So these 12 specific bugs are the red zone that threaten the to crash the system. And next we have the last one is the total issue by rule, the top 10 most frequent rules. So the tallest bar here is Rule S1808, which 162 violations. So this tells us exactly which coding standard the developers are ignoring the most. So it allows us to run targeted training to fix it. I think that's all for the Grafana. It's just to show the more clearly for the data that we got from the SonarQube analysis. I think that's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and good day, Dr. Zamri, and to all my fellow friends. I would like to continue this presentation with talking about the result that we got from the code analysis, static code analysis testing using SNYK tools. Okay, this testing is already performed, uh, which SNYK is connecting with our GitHub. Okay, with Shasha Hotel Management Local GitHub. So then we test, and then we got the results. And from the results, what we can analyze from here is SNYK already analyzed 25 files from the entire hotel management system files, and it represents as 33% from them. And from 25 analyzed files by the SNYK, they highlight 19 open issues, 19 vulnerabilities that found by the SNYK, and 19 of them is come from the PHP language. And SNOK also helped us to classify the vulnerabilities type from the 19 issues found in this hotel management system, and they have 3 vulnerabilities type. 16 of them are SQL injection, 2 of them are use of hard-coded credentials, and 1 of them is cross-site scripting. Okay, now let's recheck on SQL injections, how SNYK detecting them, and how SNYK classifying them as SN, why SNYK classifying them as SQL injection. Okay, now let's we look at here. Okay, SNYK classified line 389 from admin invoice print.php as a SQL injection with score numbers 185. This is the biggest numbers. That means this is the high risk for the systems. Okay, how it define the SQL injection, because this line shows that the developers use MySQLi query codes rather than using the prepared statements. Okay, this code MySQL query allowed the attacker to change or to record something from the database. Okay, uh, okay. Now let's we'll look at the use of hard-coded credentials, where the SNYK classified as low because the score is low, 211. Okay, let's go to the second tools that we choose for evaluating hotel management systems. Okay, right now we are choosing metrics in terms of stability. We are conducting performance testing using JMeter. Okay, JMeter is one of the open source tools that can define and evaluating the stability and the performance of hotel management systems. Okay, right now we already run the tests using the test plan. We have 7 test plans that run the performance testing on the main functions. Later I will show you. Okay, this is the result that we got after we conduct the testings. The result we visualized it. We transform it into the HTML, into the website pages. Okay, and now you can see that 96.2% of the testings are passed and 3.8% for the testings are failed. So what you focus right now is about the performance of the systems. We are evaluating the performance of hotel management system in one time. Okay, I will show you example. This JMeter actually is evaluating, for example, 1,000 people access your websites in 1 minute or in 1 second. This system can evaluate whether your website will be crashed or your website have a stable network or support entire access. Okay, and right, you can now you can see here. Okay, this is all the testing samples. Okay, this is all the test scenario. We have access homepage for admin dashboard, admin room page, admin staff page, homepage stress, homepage after login stress, and then we have room booking. Okay, staff login, staff login 1 and staff login 2, and we have user login and user setup. And you can see the samples. The samples is means you have 1,000 access in one times, and we got the average response time is 16.04. You can see here. We got the throughput, and we JMeter also analyze the network, whether the network is stable or not. Okay, because the network can show you the system will be crashed or not after 1,000 user access the system in one time. So, okay, for admin dashboard is 225 samples, and we can see the errors. JMeter inspect the errors happen in hotel management system, with the errors is 404 means that the page are not found. Okay, the page is not found, and they have 200 samples that labeled as errors because they are not found and represent as 3.80% of testing failure lah. And then top 5 errors by sampler, okay, at staff login and staff login 2. Okay, not just this logs table you can see, because JMeter also execute and convert into the CSV format, but they also visualize into the charts. You can see the charts are separated into 3 parts. Okay, we have overtime, we have throughput, and we have response time. You can see here over time, you can see all the charts. Okay, you can see response time percentile over time. You can see the active threads over time. You can see the bytes throughput over time. You can see the latencies. Latencies happen over time. You can see within all the graph for the administrative features, admin room book page, admin dashboard, the latencies are highest. Okay, the initial latencies are highest because it need to do a lot of work. Okay, so that's why it show it's more delayed rather than other features for the administrative functions. You can see the throughput, okay, the throughputs. You can see the hits per second, code per second, transaction per seconds, total transaction per seconds, response time versus request. You can see, and latency versus request. All JMeter provide all of this to be analyzed by the software tester. We already analyzed in the report, but we are unable to provide explanation, a deep explanation because of time. Okay, and you can see the response time percentile, response time overview. Okay, and then time versus threads, okay, and then response time distribution. So this is very important part. Okay, these all are very important and can assist the developer to check whether the system performance are in good or correct, are in good situation or not. So I think that's all from me. Thank you. After we finish all the testing, this section presents a consolidated overview of the code quality, security, and performance metrics collected from SonarQube, SNOIK, and JMeter. Starting with code quality and maintainability metrics from SonarQube, the table shows 363 code smells, 45 critical reliability bugs, and 1 day, 2 hours of technical debt, indicating unstable control logic despite relatively low remediation effort. The unit test coverage metric is 0.0%, which represents a complete absence of automated verification and is classified as failing. And next, the security risk metrics from both SonarQube and SNOIK reveal serious weaknesses. SonarQube reports 11 unreviewed security hotspots, while SNOIK identifies 19 critical security issues, including 16 SQL injection vulnerabilities, confirming server input validation failures in the backend modules. Finally, the performance and reliability metrics from JMeter demonstrate runtime impact. The system records a maximum response times of 16,345 milliseconds during staff login. Another stress testing with 1,000 users, the error rate reaches 100%, indicating total system breakdown. In summary, the table integrates quality, security, and performance metrics, clearly showing that structural weaknesses directly result in security exposure and performance failure, making the system unsuitable for production deployment.
For the comparison, the table shown here is the comparison between the feature-oriented quality framework from the selected article with the findings from our hotel management system project. So first, the article highlights that the system level quality matrix, it can hide critical problems. This was clearly observed in our project, where the system received a high maintainability score, which is A, yet serious security vulnerabilities and login failures were present. Second, the article emphasized that different tools reveal different quality issues. This aligns with our findings as SonarQube identifies structural issues, as NYK exposed security vulnerabilities, and JMeter revealed runtime failures. No single tool was sufficient on its own. Third, the article stresses the importance of dedicated security analysis. In our case, SNYK detected high-risk SQL injection and XSS vulnerabilities, particularly within administrative modules, which were not fully captured by general static analysis. Next, the framework suggests that runtime testing is necessary to confirm the real impact of detected issues. This was validated when the staff login feature failed completely under a concurrent load during JMeter testing. Finally, both of the article and our project show that risks are concentrated in specific features. Administrative authentication emerged as the main hotspot, and its failure represent a higher business risk than many minor issues as well. This supports the idea that maintenance should prioritize critical features rather than overall issues counts. For result consistency, this slide shows how our finding compare with the selected article. First, both studies identify feature level hotspots, meaning that quality issues are concentrated in a few critical features rather than spread evenly across the system. Second, the tools we use, SonarQube and SNYK, provide complementary insights, each are revealing different but related quality and security risks. Third, by focusing on features, we improve interpretability, helping us understand which areas are most important, both functionally and from a business perspective. Overall, our results align closely with the article, confirming that a feature-oriented quality analysis is effective for highlighting the most critical hotspot in a system. For conclusion, we can conclude that by integrating SonarQube, SNYK and JMeter, we were able to identify multi-dimensional quality issues across the hotel management system. We found that critical defects and security vulnerabilities are concentrated in specific features which are not apparent if we only look at overall quality metrics. For example, the staff login feature failed under stress testing, and there were multiple high severity SQL injection vulnerabilities demonstrating real operational risk. These findings highlight the importance of feature-oriented assessment for accurately evaluating software quality. Overall, the system cannot be considered production ready without significant remediation, particularly in the administrative modules. Based on our findings, we recommend several strategic improvement. First, fix the critical security issues such as SQL injections. Vulnerabilities must be fixed with proper input validation and secure coding practices, particularly in administrative modules. Second, the stabilized authentication, especially the staff login, should be stabilized to handle concurrent users reliably. Third, refactor and deduplicate code should be refactored, focusing on high impact features to improve maintainability and reduce risk. Fourth, automated quality gates and continuous performance testing should be implemented to prevent regressions in both security and reliability. Finally, maintenance should adopt a feature-oriented approach, prioritizing critical functionalities according to their risk and business impact to ensure long-term system stability and security.